calculate the expected holding time. So when you calculate the expected holding time at S, these are the 4 states here: healthy state, sick state, terminal ill, dead state. These are the 4 states. If you draw the stochastic process, you will draw this way: 1, 2, 3, 4 in continuous time. Okay, the time is very small here, unlike a particular duration. This is continuous time stochastic process. Okay, these are the 4 states. We are talking about this, any two. And if you want, you can write H and all that. These are given here: healthy to sick 0.02. This is not the probability, that is the transition intensity, the force of transition, you can say. Then sick to terminal ill 0.15, terminal ill to dead, this is the rate of transition. Okay, this is not the probability. Now from here to here, from dead to, there is no way we can go to healthy or sick state. From dead we can go to here. Not only that, from terminal ill also, there is no way we can go to sick state. From sick it's fine, but from terminal ill there is no way. There is only one way: it's waiting time. They say we are giving life-saving medicines in the medical terms. That means it's for some days, 3-4 days. So that is the final one. Okay, so this way it happens. Now calculate the expected holding time in state S. Then we'll do part 2 also. Maybe we have part 3, but let's discuss about this one. Calculate the expected holding time in state S. Expected holding time means, on an average, what is the time, what is the expected time one will stay in the sick state. This is what we need to find. So if you say this is 1, this is 2, this is 3, and this is 4, you need to find expected, see, holding time in this one. Wi follows exponential lambda I. Okay, so we should know W2. We are talking about holding time. Okay, W2 follows exponential lambda, and we need to find this. So if you know lambda, you will be able to write this one. But what is lambda here? If you write lambda 2 also, here I think it's the intensities are given. How to find that lambda 2? That is the question. We have lambda I, right? Let me write lambda 2 here. There is a slight difference, okay, if you compare with the Poisson process, because we consider the Poisson process with constant lambda. Here lambda I, okay, for the first state it's lambda 1, second state it's lambda 2, that way. But the Poisson process we consider, that was constant rate lambda. That is the difference. Okay, we have Poisson process with the different rate also, but we don't do those things here. So lambda 2, how to find lambda 2? That is the question. So if you remember lambda 2, what was lambda 2? You need to know the generator matrix. Let me write the generator matrix here. 1, 2, 3, 4, 1, 2, 3, 4. Okay. So 1 to 2, this is there 0.02. 1 to 3, you don't have, right? 1 to 4, yeah, 0.05. So that is minus 0.07. Okay, minus 1 to 3, are you sure it's not there? 1 to terminal ill, yeah, it's not there, but this is minus 0.07, so that total will be 0. Now 2 to 1, 2 to 1 is 1, 2 to 3, 2 to 3 is 0.15, 2 to 4, 2 to 4 is 0.05. So 2 to 2 will be minus 1.20. Is it okay? So lambda 2 will be 1.20, right? What is lambda I? Remember, we used one formula that was minus mu I. Is it? Summation j is not equal to y mu ij. So lambda 2 is 1.20. That means 1 upon 1.20. That is 120 by 100, 100 by 120, 10 divided by 12. Whatever it is, almost you can say around 1. Right? So this way we can find expected waiting time. If you know the distribution of waiting time, you will be able to find expected waiting time. But this question, this example is for a different thing. We'll go to that. Okay, mainly we'll do part 2 and part 3. These are very important when it comes to exam question. You get repeatedly similar questions that might take around 20 minutes time. We have 3 types of matrices. However, I've seen every time students, they struggle with this matrix. Okay, this is called jump chain matrix. This is normal transition matrix. This is generator matrix. There is a third one also, and we'll try to connect this one with generator matrix. These two, there is a connection between this and this. Is there a connection between this and this? That is my question. Can you find transition matrix from generator matrix? Now I'll discuss this one, and then we'll see how these two are connected. We'll see how these two are connected. We'll see now. But before going to that, I want to know this one. Is there a connection between this and this? Can you get transition matrix from generator matrix? That is the question. From transition matrix, from generator matrix to transition matrix. Can you get it given a continuous time stochastic process? So you can always find these transition matrix probability from generator matrix. And if you remember, we considered one example last time, and we found the generator matrix entries. These are the rates, intensities, the rates, okay, not the probabilities. From these we can find these. Now directly in the last class we found these. Today we'll find these from jump chain matrix probabilities. Jump chain matrix probabilities, okay. From these we'll be able to find there is a connection between this and this. So these mu ij's, the connection is this: mu ij is equal to pij. Pij, when I say these p, not these are pij's, okay. These are also jump chain pij's. These are also probabilities, but let me write differently. Let me write this way, capital P, okay. This is the formula. So don't take these pij's, okay. There is connection between this and this. I will discuss about this. What are jump chain matrix probabilities? I will discuss that. Remember, I am now giving you a class. When I leave, where I will go? These probabilities you have to write here. That's all. If I leave this one, then where I will go? That's what I have to write. Suppose I am here and I want to be here. The question is, what is the expected time it will take? Okay, suppose I want to be in this state at this time. I want to be here. I am now continuing here. I am in this state. what is the expected time it will take, okay, to reach the state k, suppose starting from I. There is a derivation, small derivation, but that's a recursion, okay. What is the expected time? If I am in I, the time it will take to go to k, suppose that is mi. I am talking about expected time, okay. The expected time to go from kth state, starting from state I, is mi. That means if you are in one state, the expected time to go to k is m1. K is suppose fixed, okay, heaven or wherever. If I is 2, expected time is m2. I3, expected time is m3. So the recursion formula says, how can you find expected time? First of all, to go here I have to leave this state. If I am giving the class, if I want to watch movie, okay, I have to leave the state. So before leaving the state, suppose if I leave the state, it's not that I will go directly here. Maybe I will go to some other state, I will stay some time, then I will go to this state, okay. First of all, I have to leave this state. So when I find the expected time to reach here, not the probability, I have to find the expected time I will stay here, okay. Before leaving I, on an average I will stay 1 upon lambda I here before leaving I, okay, because that follows, the waiting time follows wi with parameter lambda I, it follows exponential distribution. The expected time in this state will be 1 upon lambda I. Then considering that I will leave, I will go somewhere from that state j, suppose, what is the probability that I will go here from j state? Again mj, because mi is expected time to go to state k from state I. So if I make it j, from j to k you will get, okay. I means I to k. If you want to know from j to k, it will be mj, okay. So j to k, but still there is something. Once you leave I, what is the probability that you will come to j? This is what we have done, jump chain probability. Once you leave I, what is the probability that you will go to j? You might go to some other state. If you go to, suppose, nth state, so you have to write mn, right? So you have to come to j, then we will find this one, okay. So the jump chain probability we have to write capital, that is mu ij divided by lambda I or j, that was I, right? But it could be anything, okay. All possibilities you have to think. So summation will write. So what we are doing is, suppose I am here, condition that I will go here, what is the expected time it will take to go here? If I am here, what is the probability that I will go here? From here I will go here, from here I will go here. All these we are finding, okay. This is the summation. Because we are finding expected time, we have to write this. So this equation you have to use. So what you are finding here, calculate the expected future lifetime of a healthy life. Someone is in H state now, this is a healthy state, okay. So we have to find MH. Here you have to find MH. Calculate the probability, okay. This probability will find, this is probability, this already we have done. So we'll try to find MH only in this problem using this formula. So we'll form equations. These are the recursion equations we'll form and we'll solve. We'll not write summation, we'll write all possibilities in this from this example. So we will not be able to solve MH directly. It's not a left hand side, right hand side problem. From left hand side, we'll, okay, this one also you can check later. Let me write it so that it will be easier for you to check. Everything is given here. This is 1.24, but I am not interested here. Now MH I will write, this will be 1 upon lambda I, okay. 1 upon lambda I means I will start with this one. What was that? ith state, right? From healthy if you find 0.05, 0.02, okay, lambda I am finding, okay, means lambda 1 I am finding lambda 1. What is lambda 1? Mu 11, right? What is lambda 1? mh is equal to 1 upon mu 11, that is mu ij, j is not equal to I. This one plus this one I have to add, okay, that will be equal to, let me write directly, one by 0.07, okay. So once you leave this one, all possibility, this will be constant anyway, but we are forming equations, and suppose I will write 6 state, okay, then I will write ms here, then I will write md here, this one in summation, and the coefficients I have to write. The first coefficient is mu 1 to sick, you can say h to sick, okay, divided by lambda h, that one you have to write, okay. So you can check it's 0.02, see here, this one only, divided by lambda I already we found here 0.07, and this will be 0.05 by 0.07. So this is one equation, you will not get this one. Again you have to form one for MD, this one, okay. You form equation for MD, you form equation for MS, another one. So you form equation for these two, and this is there. Using all three you will be able to calculate this one, okay. Alright, then class is over. Thank you.
Thank you, sir.
Okay, fine, bye.
Thank you, sir.
Okay.